All right. Thanks, everyone. Thanks for your time, and thanks for inviting me to present here today. My name is Luke Gallagher, and I'm from RMIT University in Melbourne, Australia. And this presentation is our recent work that was submitted to CIKM and presented last month. So I have extended that talk a little bit to make it fit here. And as the title suggests, it's all about feature extraction and in the context of, say, a learning to rank system. And this work was a joint work between RMIT University and New York University with Antonio Malia, Shane Culpepper, Torsten Suhl, and Bala Kambasaglu. And just to give you a bit of context, Shane and Bala are my supervisors there, and we've done a bit of work with Antonio at New York University. All right, so just let me work out the, there we go. Okay, so just to give you a bit of context of why we care about this problem, and in particular, I'm mostly coming from an academic research perspective here, so I don't really have a lot of experience within industry working in this area. And I'm sure there are many of you in the audience which may be more familiar with the industry side of how things work in an information retrieval system. You're often dealing with users and trying to solve different problems that are really where you're trying to meet your users' needs. So yeah, just keep that in mind. And so part of the reason why we care about this, and in particular our research group at RMIT, a lot of us are interested in large-scale systems research where we want to do retrieval from large systems that is effective, but also that comes with you know, the need to be efficient as well. And there's a trade-off to play there between efficiency and effectiveness. So a lot of people there in our group, and when I say group, I mean my supervisor Shane and many of his students. So we're also interested in multi-stage retrieval systems, which is often a common scenario for learning to rank systems or systems that do some sort of ad hoc search. And we're also interested in working towards building more end-to-end type retrieval systems that we can simulate in a lab environment, because a lot of our group, again, we're interested in efficiency in data structures, and having end-to-end systems would enable us to simulate the real world in a research environment. So this diagram is an example of a multi-stage system, and this was originally presented in a talk, in a talk at SIG-IR in 2010 by Jan Petersen, and it describes the idea of the multi-stage system where in the very first stage you have a very quick, crude document selection process of candidate generation, where you might be doing Boolean matching or something like Bitfunnel, which uses a Bloom filter, or something like Wand, which is a fast version of BM25, basically. And then once you have a large candidate set of documents, you then hand them off to another phase of the system, which is mostly targeting the ranking problem. Now, I guess Bing has many more stages and many more things going on in their pipeline, which might be why we see up to 4 levels here. But for us in our work, we often think of this more simply as a two-stage system, where we have candidate generation and re-ranking or learning to rank. So just to cover what feature extraction is, I'm sure many of you already know what it is and how it works. But let's just talk about it to set the stage for some of the things to come. So I lifted this diagram from a paper that was presented in '98, and it was presented at a programming language conference. And I thought it captured the idea nicely, so I decided to reproduce it here. And so feature extraction is can be viewed as taking some sort of problem space and then converting it into a smaller problem space so that you can solve your problem more efficiently, or you can put it in another representation that allows you to be better able to learn a task or have your problem be in a more tractable format. And this actually got me thinking, and I was thinking about wanting to go as far as saying that perhaps even an inverted index itself is or does contain elements of feature extraction. It definitely sort of relates to the problem of taking a document space and mapping it into a smaller space that allows you to perform search queries at a much greater scale than you could on raw text. So yeah, it's definitely an interesting realization for me, at least. So you might find that interesting too. So the focus of this work is related to learning to rank. And I think these days, as far as I can tell, many search applications still require feature-based learning models. And the context here we'd like to think about is learning to rank and algorithm like LambdaMart or gradient boosted regression trees. These are feature-based models, and to support these in a production system, they depend on huge amounts of feature engineering and people and resources to implement the features and make sure they're correct and all this sort of thing. And they also support, they also require a lot of infrastructure around supporting feature extraction during the retrieval process. And so I think because of this is something that we don't, or this is something that we tend to avoid from a research perspective or from an academic perspective, as compared to an industry perspective. Because whereas industry is really doing these things because they need to support their users, and the user needs to receive their information need very quickly. So, but in academia, I guess there's not a huge return on investment for us to spend a lot of time doing feature engineering. So that doesn't really help us get a paper published in the short term. So from that angle, I think it's been unfortunate from a research perspective that we've been, we've been sort of overlooking this work in a way, and it has set a really high bar for us to investigate things further. For example, our group is interested in efficiency, and to do work on efficiency and feature extraction, there's a huge upfront cost for us to get to that point. So I think that has been an unfortunate aspect of the research side of things. Just one moment, I'll just fix something here. Sorry about this.
Look, I will take the occasion to tell you there's a sort of gray rectangle. I think maybe it's the Zoom chat or something if on the right side of your screen.
Okay, great. Thank you.
So if you can move it probably, or yeah, that... Brilliant.
Okay.
Thank you.
Whoops. Is that better?
Definitely. Thank you.
Great. Yes, just to so now to sort of step back and look at feature extraction in learning to rank specifically. I guess we have a lot of decisions to make about this. So you have to decide which features you want to implement or extract. And the features that you're implementing may depend on the search task. There are many good ranking features that depend on both the query and the document. And what this means is that in general, if you're running a search system, you're always going to have some fraction of queries that you've never seen before. So pre-computation and caching can get you so far, but you have to also be prepared that you're going to see queries that you haven't seen, and therefore you can't pre-compute these ones. And what this means is that you need to have the infrastructure and support to run feature extraction at runtime, I guess, in a live setting. Again, this is all an academic viewpoint, so there may be many other tricks and things that industry has developed to help deal with these problems. That I'm not aware of, but yeah, I would be interested to hear from some of you how you might deal with some of these problems. Okay, so here's a very simple diagram of what I would call a multi-stage search system. It's really just a basic description of candidate generation and re-ranking. And so the user submits a search query, and then a candidate set of documents are generated fairly quickly with something like WAND or BM25. And then that's handed off to a feature extraction process, which I've highlighted in blue here. And the feature extraction process may need to retrieve data structures from an index and then compute various features. And then the output of that is some form of query document vector. And that's all handed off to a re-ranking component. In this case, it's learning to rank, and it can reorder the top results and return them to the user. So the work that we're contributing for the CIKM paper, that's dealing with feature extraction. So I've highlighted this area. This is sort of the scenario that we'd like to think about at runtime, and I guess this could give you some context of how we think about the feature extraction process itself. There are elements of where you have, say, static features or features that can be pre-computed. They are just sitting around in an index, but others have to be computed on the fly. So with this diagram in mind, this is how we've thought about it, and perhaps how we've sort of tackled solving this problem from this aspect. Okay, so just to highlight the key contributions that we are providing in this work. One is some software around feature extraction. So yeah, one of the main goals is to try and make it easier for people to test out their ideas around feature extraction rather than spending their time doing feature engineering or supporting the infrastructure to do it. So that's one of the goals to making this open and accessible to the public. And overall, we get to have perhaps a better ability to simulate our search tasks in a larger picture or a larger research environment or retrieval system, which may be dependent on feature extraction. And the second thing is we used the software, the feature extraction tool that we built to release a learning to rank dataset, which we built on the Clue Web collection. And I'm not sure if this is true, but I was thinking about this the other day too. And out of all the learning to rank datasets that I've used, the main ones being Yahoo, the MSLR dataset, there's the iStella dataset as well, from Italy. All of these datasets in some way, shape or form have some information missing. So for example, the Yahoo dataset, it is missing many of the features, what the actual features are, and you don't know what the queries are, and you really don't know what the original documents are either. You know maybe one or two features from that data set. One is BM25F-SD, but that's about it. So it's pretty hard to say you wanted to reconstruct that data set in another environment or test out things in a different way. It's very hard to do anything else in different scenarios. The MSLR one, for example, you know what all the features are, and many of them we re-implemented in the software, but we don't know what the queries are, and we don't know what the actual documents are. And it's a similar scenario for the iStella dataset as well. So here I'm claiming that this may be, I'm not sure on this, but it might be one of the only datasets around where you know what the queries are, you can have access to the original documents, you know what the features are and how they're implemented, and these sorts of details. So I think that is a good example going forward and may help for future work in this area. Excuse me. So part of the process that led us down this path was that we originally wanted to do some multi-stage retrieval experiments on a collection that we had access to, and we ended up realizing that we had to implement all the features ourselves. And along the way, we did look around at existing systems, existing published work, to see if there was any way forward there. And also we were looking around for implementations of features and reporting on features and things that were used in the literature as well. So, but what we found was that while there are many great tools and software out there that is open source, and they are made by very smart people, we found in general we didn't really seem to find software that provided implementations of large sets of features or tried to support feature extraction in a pluggable way. For example, the software like Solar, Elastic, and Terrier, these are all really great pieces of software, and they do support learning to rank and I guess feature extraction in some sense, but their role is to have a retrieval system. Their role isn't really to sit around and do feature engineering for people or implement sets of features, which makes sense, right? It's a very resource intensive problem, and everyone's search problem may be slightly different. So it would be really hard to put down on paper in the general case for all the various people that would be using this software in practice. Another system, Mansorini, which I believe is built on Lucene as well, provides a small set of features and some learning to rank, but nothing really it didn't really have the extent that we were thinking about. But it is one example that does provide some features and learning to rank out of the box. And also, much of the prior work is really made for the publication, or so I just call it single-use engineering, where they made their retrieval system or implemented a small set of features just for their system, and they didn't really support that software or release it in a way that was easy to use. So that led us to the conclusion that we don't have a large set of open features that we can easily use and helps facilitate the feature extraction process, or lets you have the ability to run feature extraction experiments in isolation, or allow you to perhaps integrate that into a larger system and think about having a large system in a lab environment, or being able to run end-to-end experiments. Again, this is coming from an academic viewpoint, so I'm sure industry has solved some of these problems really, really well. And they have internal tools and toolkits to probably do and analyze all this sort of stuff. But it's just something that we haven't really seen out in the open very much. So now I'll just sort of briefly introduce the software that we released for this work. The software is called FXT, and that just stands for Feature Extraction Toolkit. And it comes with a large set of features, and you can pick and choose which ones you want depending on what you're doing. And most of the features at this point have been derived from the literature on query performance prediction and also learning to rank. And most of these implementations were motivated by people in our group that had some research project, and they were using a feature-based model, and they had to implement a bunch of features to get that model to work, or their research idea to work. And so slowly we have sort of aggregated this work here into this toolkit. So that's why we have a lot of query performance prediction features and a lot of features targeting learning to rank at this stage. That can definitely change or be added to in the future. That's just where we're at right now with this. The software itself is centered around two components. An indexer, obviously. So an indexer takes an existing, at this point, in the software, the indexer can only take an existing injury index, and it will convert that into an optimized index for feature extraction. So more specifically, a field-based index, because we like to take advantage of the document structure. And I guess I should also point out for context, that a lot of the features are targeting, HTML and the document structure around that. But we are working on supporting the common index file format, CIFF, which may be an easier way to ingest indexes from other systems and help reduce the engineering effort on supporting a large range of different search systems. The other component is the extractor. So the extractor really just takes a set of candidate documents. If you're familiar with the Trek run file, it takes an existing Trek run file, which has the query IDs, the document IDs, the stage, the candidate generation score from the candidate generation algorithm. And it takes a set of queries, and then it will take the queries and the Trek run file, so the list of candidate documents, and extract features for all those query document pairs. And then the output of that is just a CSV file. So that's one way you might just generate training data for learning a model or something like that. It also would be the place where you can do efficiency experiments on certain features or all features, if you just want to do some isolated efficiency experiments. And I guess, yeah, that's the extractor process. And so I think I've described some of the use cases in that. And, we're working towards end-to-end retrieval experiments, but at this stage, I think there needs to be a bit more work on the API and support around the software to make that easier to integrate. So that's something that's still in progress, but it's definitely something that we're thinking about with this software. Just to give you a summary of the features within the software itself. So the term score aggregation features, they are the query performance predictors. And then we have query document scores, which are your classic retrieval models, but it also includes retrieval models over various fields in the document, like the title or the heading or the inlinks or the A tags, things like that. And then we have some proximity features, which are diagram versions of those. And then we have a number of static document quality features, a large number of which were from Michael Bendesky when he was doing his PhD at UMass. And then we have a number of query-only features. Yep. So now to move on to the second resource that was a part of this work, which is the Learning to Rank dataset. We provided, what we did was extract a number of features on the ClueWeb dataset for the web tracks over the 4 years from 2009 to 2012. We selected a bunch of features, which was basically ignoring the query performance predictors. And we made this publicly available as well. So you can download and use this data set, and you can also go and get the code that we use to build the data set if you would like to reproduce it from scratch. And I guess, what's the other thing? Oh yeah, this note about reproducibility, that's just something that's more academic. from the ACM on their definitions, but I don't think that's really as applicable here. And to give you an idea of the features in the data set, so you can see that we have the similar features with the query performance predictors removed. And we also added the Alexa rank score in this case because that's not really a feature that is generated. We went and found some Alexa rank scores from 2010 to use in this data set as well. So overall, the dataset construction process is to take an INRI index with fields and then use FXT to convert that into the feature version of the index, generate a candidate set of documents with BM25, and then extract the features. And then we shuffled up the queries and made various train valid test sets over the 4 different years. So there is a few things to note about ClueWeb and the various relevance judgment methods that we used over the years. So in 2009, there was a number of different judgment methods used. MQ09 here is the million query track in 2009, and WT09 is the web track 09. And these two tracks shared a set of judgments for that year. So that's important to understand. And the other important thing is that there are different grade levels or different labels used across the various years, which may or may not impact our results. And there are, I guess there's various things to try here that we haven't looked at, which is like label folding or label smoothing or something like that to see how things play out. But for this purpose, we just left the grades as they are. And you'll see why in the next slide, how things are split up. So, so the training and test sets for the various years. So we have 4 sets of test queries for each year of the ClueWeb track. And you can see that for the 2009 queries, we used the million query track queries for training on the web track 2009 queries. I think that's the main thing to point out here. And that's due to the judgment methods that were used. And then for the remaining years, we just fall back into a standard cross-fold validation style there. Although note that the different grade levels are mixed in, so that may be a factor to think about for future work. So if you spend any amount of time working with a data set, you eventually find some sort of issue with it. And ours is no different. The SCM feature was broken, which we unfortunately found out about after camera ready, but the good news is that we versioned the data set. So we're working on fixing up this feature, and then we can just release the data set as a new version. And the idea is that people that use the data set in the future, they can just report which version they use, so we can still compare results. Okay, so this leads to our experiments that we ran for this work. And I have to say that they're quite bland. Like, there's not a lot of depth to the experiments that we ran because we spent a lot of time working on the software, on the feature extraction part, and on getting the data set right. So we just ran some fairly simple experiments which just compare the effectiveness of a learning to rank model on the data set compared to some traditional baselines like BM25. And we also use the each year use the best submission from the TREC from the track that was run each year. And we can compare to that one too. So the other important thing is that we evaluate on each of these ClueWeb query sets individually. Some I have in the past evaluated all of the topics together. And now that you see the different grade levels shown in the table earlier, it's good to note that we should be evaluating each of these query sets individually for each year. So this graph shows you the effectiveness results on ClueWeb. On the x-axis, you can see each year is grouped there. And on the y-axis, we have NDCG at 20. Now, NDCG at 20 because that was the metric of choice, I believe, that was used for the tracks when they were run. And so I was just keeping keeping in line with that there. And what you can see is that LambdaMart is mostly more or less doing better than the traditional baselines like BM25 and SDM. And it's not very surprising because the LambdaMart model has access to various versions of BM25 and it has access to SDM, although SDM is broken. But what we also see is the best trek model. And we've included that there as what an upper bound on effectiveness might be. And it shows that in some cases, the LambdaMart model is able to get quite good or quite comparable effectiveness to some of those submissions, which really just sort of verifies that it's working, the model is working, or it's using features that are helping it gain effectiveness. So that's all looking okay. And the second thing we looked into was as the feature importance. So we trained 4 models, and here I've just aggregated the feature importance across the 4 different models and listed the results here. So you have the importance on the x-axis and the name of the feature on the y-axis. And what we can see here, if we just say look at the top 3, we have a field-based feature, which is a title-based feature, is one of the most important features, which is just your language model or query likelihood. And then we have BM25, which is from the candidate generation process. And then we have a static document feature. And that, and we note that there's no proximity features or no term dependency features in these top results. And this also, I guess, confirms or highlights that something might be wrong, which as to why SDM is missing from this list. So, so that's a very basic introspection of say feature importance, but I would be really excited to see more work in this area of what other people might be able to do with model interpretation methods and things like that, and sort of give us more understanding about different features and how they work in different, I guess, for different queries and different data sets. That would be interesting to see. Okay, so just to give you an overview of what we discussed, we released 2 resources as part of this CIKM paper, and that was the FXT software and the Learning to Rank dataset on ClueWeb. And overall, we hope these things facilitate more open and accessible research and provide new ways or stimulate ideas about how to bring the research or the academic side of things and the industry side of things closer together. You know, it's always interesting to hear ideas from both sides, both viewpoints, I think. And just some ideas for future work would be obviously efficiency studies in feature extraction and in the context of end-to-end systems, model interpretation, as I just mentioned, and another thing that we really haven't seen in the open very much is because it's one, intractable, and two, I guess, takes a lot of work, is the idea of feature selection and how features work for different learning tasks and what features are actually redundant and things like that. So yeah, so I think I'll stop there, and I'd just like to say, yeah, thanks for your time and thanks for your attention today. So thanks very much.
Thank you, Luke. So what we will do next will be to give the possibility for questions. So anyone with questions, please write a message in the chat, and then we are going to address few of them in the next like 5-10 minutes on a first in, first out manner. So in the meantime, people write their questions. I have one. Actually, I have a couple of them, but let's start with this one, Luke. So what kind of tool have you used for the feature importance evaluation?
Yes. So that was just calculating the number of times the feature was used in a model. That's basically the basis of feature importance. And I believe I just used a function straight out of the LightGBM API. Okay.
Perfect. Have you evaluated by any chance the possibility of using libraries such as a tree shop, for example?
Yes, I've heard of that one, but I have never used it in my work just yet. But that has been on my list to look into at some point. Yes.
Okay. Okay.
Yeah.
Because we use it, and it can give you like quite a lot of possibilities of exploring like feature importance. So.
Okay, great.
It can be interesting.
Okay, thank you.
Okay, in the meantime, I don't see any questions yet, so I will go with the next one. So please, if anyone has any, write in the chat so that we can pick them up. My next question is about, you mentioned an INDRI index that was the initial index you used. I'm ignorant about that. Is it like an inverted index implementation, or?
Right, yes, so it has, yes, it has an inverted index, and if you store the documents, it will build a direct index as well, which is just, you know, the term positions of all the documents if you want to do proximity search or things like that. And then it has other data structures for inverted indexes over fields as well. So I think that's generally the main index structures. Yeah.
So the FXT software is able first to do the feature extraction and generate the training, test, and validation sets you like. And what about the query time? So once you deploy the model to, I don't know if you tried on any search engine on the same maybe INDRI platform, because I was wondering like if you use the FXT also at query time, so to extract features at query time and then evaluate both performance and the integration.
Right. Yes. So, so that's a bit of a rough area at the moment. So there's no real proper API that makes it easier to do that. I mean, it's definitely doable, but there needs to be a bit of work. There would be a bit of engineering effort in getting that to work right. But what we have done in the past is a paper that we released in SIG-IR 17. We did an efficiency analysis of the feature extraction process, but that's as far as we got. So we ran the feature extraction component with efficiency timings, and that's as far as we needed to get for that project. So the integration aspect definitely needs more work, and it's is something that we're working on. So we haven't actually been able to test an end-to-end query time solution altogether. One other possibility might be, you know, like one of the ideas that we had to test this out would be to have, say, something like PISA, which is a sort of candidate generation retrieval system. So it just deals with the candidate generation process, and then have that hand things over to FXT, and then have FXT hand things over to your, whatever your learning to rank setup would be. But we're not quite there yet, unfortunately. Yeah.
Makes sense. Anyway, it's kind of inspirational, because in Solar currently we leave the responsibility of feature extraction to the administrator, let's say, to the user. So if you have like a field which is title, and you want to generate the title BM25, for example, or any kind of more advanced feature, is only responsibility of the admin. You can't just, for example, select, I want to extract A, B, C, D, F kind of features from title and the, I don't know, the query, for example, in case you want query document features. So it would be actually quite cool to take a look to your set of features, and also try to see how it's possible. I'm talking about Solar just because I'm a Solar committer, but anyway, in open source frameworks, to integrate that in a way to ease the process for a user, and also to inspire the user, because sometimes you have the title field, but you don't know, you have the title, you have your query terms, but you don't know the 100 kind of features that academically have been tested to be generated from those two elements. So, you know, maybe one would just do a BM25 and maybe that's it, but there are many more. So yeah, definitely an interesting things to explore.
Yeah, great.
So I don't see any other questions. So Luke, thank you very much for your presentation.
Yes, thank you very much.